HippoRAG. What if your retriever remembered like a brain? Let's dig in. Quick recap before the fun starts. In Module 3, Microsoft GraphRAG gave us beautiful global answers, but it paid for them with expensive offline community summaries. In Module 4, LinearRAG made things cheap and incremental, but its retrieval was mostly a one-hop neighbor gather. Today's question is the obvious next one. Can we get true multi-hop reasoning across scattered documents in a single step without any of that offline summarization cost? HippoRAG says yes, and it gets the idea from your own brain. Here is the pain. Imagine a question whose answer is spread across 3 different documents that never mention each other directly. A standard vector retriever grabs whatever looks similar to the query and usually misses the connecting pieces. The classic fix is to retrieve, let the language model think, retrieve again, and loop, sometimes many times. That works, but every loop is another expensive language model call. HippoRAG wants to integrate knowledge across those disparate, non-contiguous documents in a single shot. So the authors from Ohio State did something clever. Instead of inventing a new trick, they copied a system that already solves this beautifully: human long-term memory. Cognitive scientists have a model called the hippocampal indexing theory, which describes how the brain stores a memory once and then recalls the whole thing from just a tiny fragment of a cue. HippoRAG is quite literally an engineering tribute to that theory. Let me animate the analogy because it is the heart of the whole method. Human memory uses 3 cooperating parts. The neocortex stores general world knowledge and language. The hippocampus is a tiny index that stores associations between memories. And the parahippocampal region routes a partial cue to the right index entry, even when the wording is fuzzy. HippoRAG maps each one onto software. The neocortex becomes the large language model, the hippocampus becomes a knowledge graph index, and the parahippocampal region becomes the retrieval encoder that handles synonyms. Hold on to this mapping. Every piece coming up is just one of these 3 boxes. HippoRAG runs in 2 phases, exactly like memory does. There's an offline phase where you read everything once and build the index. Think of this as forming memories. And there's an online phase where a question arrives and you recall the relevant pieces fast. We'll walk the offline build first, then the online recall. Keep that split in mind. It maps cleanly onto indexing versus querying. Offline step 1, read every document and pull out facts. HippoRAG uses open information extraction, the same open IE we met back in Module 2, to turn sentences into subject-predicate-object triples. Steve Jobs co-founded Apple becomes a clean little fact. Each triple gives us 2 entity nodes and 1 labeled edge. The big design choice here is that it's schemaless. Unlike the rigid medical schema we built in Module 2, HippoRAG imposes no fixed vocabulary, so it can absorb any domains straight out of the box. Do that across the whole corpus and you get one big entity graph, thousands of named things, wired together by the relations that actually appeared in the text. This is the artificial hippocampus, a web of associations rather than a pile of isolated chunks. But there's a crack in it, and it's the same crack that breaks naive retrieval. Here's the crack. One document says USA. Another says United States. To a human, these are obviously the same thing, but in the raw graph they are 2 completely separate nodes with no edge between them. So a path that should connect through that country is silently broken, and your multi-hop reasoning dies on a paraphrase. This is exactly the kind of fuzzy cue matching the parahippocampal region handles in the brain. Here's the fix animated. HippoRAG runs every entity phrase through a dense retrieval encoder, the same kind of embedding model we've used all course, here Contriever or call Birdie v2. That turns each phrase into a vector. Then, for any pair of entities whose vectors are more similar than a chosen threshold, it inserts an artificial synonymy edge linking them. USA and United States now sit a single hop apart. This is the parahippocampal region's job in code: stitch the surface variants together so no path breaks on wording. That threshold is a real knob, and it's a balancing act. Set it too low and you start linking things that are merely related but not the same. Apple the fruit gets fused with Apple the company, and your graph turns to mush. Set it too high and you miss genuine synonyms, leaving paths broken. Tuning that single number trades precision against recall in the associations, which is a theme you'll recognize from every module so far. Let's freeze the offline build in one frame. Documents go in. OpenIE pulls triples and assembles the entity graph. The dense encoder adds synonymy edges across surface variants. And that's it, no community detection, no laden, no per-community summaries written by the language model. Compared to the Module 3 pipeline, the indexing here is deliberately lame. The expensive brain-like work is saved for query time where it belongs. Index built. A question arrives. Now we switch to the online phase, recall, and this is where HippoRAG earns its name. The goal is to light up exactly the entities relevant to the question, even the ones several hops away that the question never names, and to do it in a single computation. 3 quick steps get us there. Steps 1 and 2 are quick. The language model reads the question and extracts the named entities in it, from which Stanford professor studies Alzheimer's. It pulls Stanford and Alzheimer's. Then the same retrieval encoder we used for synonyms matches those phrases to actual nodes in the graph. Those matched nodes become our seed nodes, the partial queue, the fragment of memory we start the recall from. Step 3 is the trick. Instead of walking the graph hop by hop with the language model in the loop, HippoRAG releases probability from the seed nodes and lets it spread across the edges, like dye diffusing through water or activation spreading through neurons. Nodes that are strongly, repeatedly connected back to the seeds soak up a lot of probability. Distant, weakly linked nodes get a little. When the spreading settles, the probability on each node is its relevance score. That settling is computed in one shot by an algorithm you've heard of, Personalized PageRank. Quick refresher because PageRank is the engine here. Picture a random web surfer clicking links forever. PageRank is just the long-run fraction of time the surfer spends on each page. Well-linked, important pages get visited more. Every so often the surfer gets bored and teleports to a random page instead of clicking. That teleport keeps the math stable. Standard PageRank teleports uniformly to any page with equal chance. Now watch what one small change does. Here's the one change that makes it perfect for us. In Personalized PageRank, the surfer doesn't teleport to a random page. They always teleport back to our seed nodes, the entities from the question. So the surfer keeps getting yanked home to the query and wanders out from there. The result is that nodes near the query, in graph association terms, accumulate high probability and irrelevant far-flung nodes don't. It's a query-biased importance score. Let's make that precise with the equation. Here it is on white term by term. The score vector R equals D times M times R, plus 1 minus D times P. M is the transition matrix of our entity graph. The normalized connections D is the damping factor, the chance the surfer keeps walking. 1 minus D is the chance they teleport. And P is the star of the show, the personalization or reset vector. In plain PageRank, P is uniform. In Personalized PageRank, P is concentrated only on the seed nodes, the query entities weighted by node specificity. Solve for the steady state and you get this closed form, R equals 1 minus D, times the inverse of I minus dm times P. One linear solve and every node has its query relevant score. No loop. Sit with why this is so neat. The matrix M encodes one-hop connections. But when you solve that equation, you're effectively summing walks of every length. 1 hop, 2 hops, 3 hops, all of them, in a single algebraic step. So a fact 3 documents away, reachable only by chaining relationships, still gets probability flowing to it. That's genuine multi-hop reasoning, but instead of the retrieve-think-retrieve loops we saw with drift and IRCOT, it falls out of one matrix computation. Let me run the whole online recall on one question, animated. The question is, which Stanford professor studies Alzheimer's? We extract the seeds Stanford and Alzheimer's, light them up, and start Personalized PageRank. Probability spreads outward, repeatedly restarting at those 2 seeds. It flows through the lab nodes, the publication nodes, the people nodes, and converges with the highest mass on one entity that both seeds reach, Thomas Südhoff, the Stanford neuroscientist linked to Alzheimer's research. We never told the system his name. The graph in a single page rank solve found him. That's pattern completion. One more refinement keeps PageRank honest. Some nodes are hubs, generic entities like country or study that connect to almost everything. Left alone, probability would pool on these boring hubs and drown out the signal. So HippoRAG weights each node by its specificity, an idea borrowed straight from inverse document frequency in classic search. A node that appears in few passages is rare and informative, so it's boosted. A node that appears everywhere is downweighted. That weighting feeds into the seeds, so the spreading favors discriminative entities, not popular ones. The last online step turns node scores back into documents. Each passage in the corpus contains some set of entities, and each of those entities now carries a PageRank probability. HippoRAG sums or pools those node scores up to the passage level, ranks the passages, and hands the top few to the language model to read and answer. So the brain, like graph diffusion, does the reasoning, and the passages it surfaces give the model clean, connected evidence. Let's place HippoRAG next to its neighbors. Versus Module 3 Microsoft GraphRAG, HippoRAG skips the expensive community summaries entirely. Versus Drift and Hierarchical T-style iterative retrieval, it replaces the multi-round language model loop with one PageRank solve. Versus Module 4 LinearRAG, instead of a one-hop key-value merge, it diffuses across the whole graph, so it reaches genuinely distant facts. The common thread, HippoRAG, moves the cleverness out of repeated language model calls and into a single cheap piece of linear algebra. Does it actually work? On the hard multi-hop benchmarks, MuSequa, 2Wiki multi-hop, and HotPotQA, HippoRAG beats the previous best by up to 20%. And its single-step retrieval matches or beats iterative methods like IRCOT, while being 10 to 30 times cheaper and 6 to 13 times faster at query time. That cost gap is the whole point. You get multi-hop quality without paying for multi-hop loops. Combine HippoRAG with IRCOT, and you can push the numbers even higher. Now the honest caveat that sets up the sequel. The original HippoRAG is brilliant at associative multi-hop questions, connecting distant dots. But by routing everything through entities, it can actually do worse than plain vector RAG on simple factual questions, where the answer is just sitting in one passage and there's no hopping to do. Augmenting with a graph helped sense-making but hurt basic recall. The authors fixed this in a follow-up, and it's an elegant fix. Here's HippoRAG 2 animated. The fix is to stop treating passages as second-class citizens. In version 1, the graph held only entity nodes, and passages were scored afterward. In version 2, the text chunks themselves are added directly into the graph as passage nodes, each one linked to the entities it contains. That gives a richer, two-kind graph, entity nodes and passage nodes together. Now, when Personalized PageRank runs, the passage nodes take part in the diffusion directly, picking up steady-state probability of their own. So a passage can be retrieved because of its own activation, not just borrowed from its entities. Factual recall recovers and associative power stays. 2 more touches in version 2. The passage integration is deeper. Passages aren't bolted on at the end, they're woven into the diffusion, which is why the paper is titled From RAG to Memory. And there's a recognition memory step, a smarter online use of the language model to filter which triples and passages actually belong in the context before they crowd it. The payoff is a system strong across all 3 kinds of human memory, factual, sense-making, and associative, with about a 7% lift on associative tasks over the best embedding model without the factual regression that hurt version 1. Enough theory, let's build it. The wonderful thing about HippoRAG is that there's an official library that wraps this entire brain-inspired pipeline into about 3 method calls. Before we touch any code, though, let's meet that library properly, what it is, what objects it gives us, and which knobs map onto the neocortex and the parahippocampal region we've been talking about. Meet the libraries. It's an open-source Python package from the Ohio State NLP group, and you install it with a plain pip install HippoRAG. It hides all the moving parts we've discussed: the OpenIE extraction, the entity graph, the synonymy edges, the personalized PageRank solver behind one class. You give it two models and a folder, and it handles the rest. Think of it as the assembled brain. You just have to plug in the cortex and the encoder. Here's the constructor, and notice how the brain analogy shows up right in the arguments. We import the HippoRAG class, then create one object. SaveDire is just where the index lives on disk. LLM model name is the neocortex, the model that does OpenIE and writes answers. Here, GPT-4o Mini. And embedding model name is the parahippocampal region, the dense retrieval encoder that builds synonymy edges and matches query entities to nodes. Here, NVEmbed v2. If you're self-hosting, there are matching base URL arguments to point at your own endpoints. Two models, one folder. That's the whole setup. Three methods do everything. Index takes your list of documents and runs the entire offline build. OpenIE, the entity graph, the synonymy edges. In one call, Retrieve takes your queries, runs personalized PageRank under the hood, and returns the top passages with numRetrieve as your K. And RAGCA takes those retrieval results, or just the raw queries, and produces final answers, with an optional evaluation mode that scores against gold documents and answers. Index, retrieve, answer. That's the brain-inspired pipeline in 3 lines, and now we'll run them end to end. For the lab, let's use a tiny corpus designed to need multi-hop reasoning, so we can actually see HippoRAG shine. 3 short passages. One says Thomas Sudhoff is a professor at Stanford. Another says Sudhoff's lab studies the molecular basis of Alzheimer's disease. A third mentions Stanford is in California. No single passage answers which Stanford professor studies Alzheimer's. You have to chain the first 2. Perfect test for spreading activation. Step 1 of the lab, build the index. We construct the HippoRAG object with our 2 models and a save directory, then drop our 3 passages into a docs list and call index on them. Behind that single call, the library runs OpenIE on each passage, extracts entities like Thomas Sudhoff, Stanford, and Alzheimer's, wires them into the entity graph, and runs the dense encoder to add any synonymy edges. When it returns, our artificial hippocampus is fully formed and saved to disk. Step 2, retrieve. We pass our multi-hop question to retrieve and ask for the top 2 passages. Inside this call is everything we spent the module on. The language model extracts Stanford and Alzheimer's as query entities. The encoder matches them to seed nodes, and personalized PageRank spreads activation across the graph in one solve. The passages come back ranked by their node's steady-state scores. And crucially, passage 1 about Sudhoff at Stanford and passage 2 about his Alzheimer's lab both surface, even though neither alone matches the query well. Step 3, get the actual answer. We hand the retrieval results to RAGCA, which feeds those top passages to the language model as evidence and asks it to answer. Because the right 2 passages were retrieved, the model can chain them. Sudhoff is at Stanford, Sudhoff studies Alzheimer's, and reply Thomas Sudhoff. And there's a one-liner shortcut, call RAGCA directly with the queries, and it does retrieval and answering together. That's the full HippoRAG pipeline, index to answer, running end-to-end. Step back and see what those 3 calls demonstrated end-to-end. We built a schemaless entity graph with synonymy edges from raw text. We ran a single personalized PageRank solve to do multi-hop retrieval. And we got a correct answer that required chaining 2 passages, no single chunk contained. That's the entire chapter, executed hippocampal index, spreading activation, single-step recall, in well under 20 lines. So when should you actually pick this off the shelf? Reach for HippoRAG when your questions are associative and multi-hop, connecting facts scattered across many documents, and you care about query time, cost, and latency, because the single PageRank solve is dramatically cheaper than iterative loops or community MapReduce. Use HippoRAG too when you also need rock-solid simple factual recall in the same system. And if your corpus changes constantly, remember Module 4 LinearRAG is still the incremental update champion. Different tools, different jobs. Let's lock it in. HippoRAG borrows the brain's hippocampal index, a schemaless OpenIE entity graph, stitched together with synonymy edges from a dense encoder, and queried by personalized PageRank that spreads activation from your query entities to do multi-hop retrieval in a single step. No community summaries, no iterative loops. HippoRAG 2 folds passages into the graph for balanced factual and associative memory. Next module, LinearRAG takes the efficiency obsession even further, a relation-free graph built with zero language model tokens. See you there.
If you like this video, please subscribe and share. Thank you.